Well, g'day everyone. Welcome to Theory Thursdays. This hopefully be a regular gig, maybe not every Thursday, but I'm starting to do quite a few of these live streaming sessions. And this week I've been doing one every day, really just as a bit of a helping hand to all those in lockdown at the moment, particularly in Metro Melbourne and now in Auckland. Where there are a lot of people who can't work but want to make use of their time could benefit from doing a bit of theory. So we've covered batteries and system design a little bit this week. You can catch up on all of those by just going to my YouTube channel. It's just YouTube/Smart Energy Lab. And you can see all those previous live streams. Today's kind of a special one. I'm doing it for all my Kiwi brothers over there in New Zealand. I'm actually a Kiwi myself, who are in lockdown, and I had a special request from a friend in New Zealand, and she was saying that it would be good to do something for those who are just entering or just thinking about starting off in solar. New Zealand hasn't had quite the speed of uptake that Australia has, which is where I live these days, but it's a strong market and it's growing. And because of the way regulations work, there isn't compulsory training in New Zealand like there is pretty much in Australia. You really have to volunteer yourself to do that training. So, like many things, I certainly do it this way, use YouTube to find out how to do stuff. So today we're going to go through some of the basics of how PV works, the photovoltaic principle, a little bit about the history of photovoltaics, and a little bit about the characteristics of a solar panel and their manufacture. Tomorrow I'm going to get a bit more into the mechanics of solar, things like DC isolators, voltage rating of components, cable selection, a bit more the sort of installer's hardware side. But today's really just a theory focus, and we'll dive into that. So let me just bring up, I've got a slide deck here, and I'll be talking through this and jumping in and out. I love comments and questions. G'day David, someone said hello to me already in the comments, that's great. So please feel free to type some comments in or questions, and if it's something that I'm not going to cover today, I'll probably use it for future sessions, so please put your wish list of what you'd like to learn about in the comments as well. So let's just go over to my presentation. So here we are. This is where I live, by the way. For those of you who haven't seen my sessions before, I often start with a pretty picture of Mount Turley-Buwong. It's a really beautiful mountain. It's about an hour and a quarter from Melbourne CBD out in the Yarra Valley, which is kind of the wine-growing district of eastern Melbourne. We're up at 700 metres and it gets pretty cold up here. We had a nice dusting of snow, about 10 centimetres a couple of weeks ago, so that was pretty nice. I also do a lot of testing as well as training. So I do testing of equipment here, field testing of solar, battery, smart energy systems. And I used to do a lot of face-to-face training until COVID sort of made that a bit impractical. So hence I'm online more or less every day, doing webinars, training, streaming, talking to people. So let me see if I can just move through these. Where did it all start? Well, you might find this hard to believe, but the photovoltaic principle started way back in 1839, well, discovered in 1839 by a young French physicist. This is Mr. Becquerel. Actually, he was only about, I think, 18 or so when he discovered the photovoltaic effect. He noticed in a liquid of green goo or something, when light shone on it, a very small current was produced. So it wasn't a silicon cell. The photovoltaic effect can occur with lots of things. Lots of materials can exhibit the photovoltaic effect. So it wasn't just a silicon cell. So we've also got, hang on, I'm just going to move myself down a little bit here in the screen so I'm not covering up Mr. Becquerel. There we go. So Albert Einstein, he was awarded the Nobel Prize in physics for explaining the photovoltaic effect. A lot of people think he got it for something to do with E equals mc squared, but no, it was describing the photovoltaic effect back in 1921. It was a pretty big jump in the understanding of how the energy of light was converted into electricity. So well done, Albert Einstein. We didn't really have a use for that phenomena, though, for the photovoltaic effect, which I just shortened it to PV, it's easy to say, till 1950s. And that was because we came up with a low cost, well, in those days it seemed very expensive, but by today's standards, but it was low cost way of producing some electricity from the sun's light. And that was the silicon revolution. The semiconductor revolution brought with us in 1955 the first PV modules. I mean, we're talking efficiencies of just 1 or 2%. So they're incredibly inefficient, but they worked, and they're incredibly expensive. As you can see from this slide, the first commercially produced ones were US $1,784 a watt. Now, if you're trying to think what that means in today's terms, well, a 1 kilowatt system would cost you $1.78 million. A 5 kilowatt system, 5 times that. So just insane cost back in 1956. But like with many things, when volume goes up, prices come down. And so we saw a really big drop in the price of PV in a very short period of time. But even still, it was still pretty expensive. Here we've got a lighthouse in Japan, and it was the biggest system, not the biggest panel, but the biggest system in the world, 242 watts. Kind of makes you laugh these days when that's considered a small solar panel. But it was cost effective. Even back then when they were paying a tremendous amount for those solar panels to be manufactured, it was still cheaper than a manned lighthouse with a diesel generator, refueling regularly, all of those ongoing costs. So PV got a leg up with remote area, where the cost of maintaining an electrical generation system in remote areas was very high. And that's where Australia really got started too. We were an early adopter of PV for telecommunication and lighthouses, etc., in remote areas. Then in 1982, we saw some of the first large-scale solar going in sunny and rather wealthy parts of the world, California. So a megawatt-scale plant with 108 dual tracking solar panels. Now, if you wonder what dual tracking means, it means it follows the sun from morning to night, and it also adjusts for seasonal height differences in the position of the sun from summer to winter. So it's quite a complex tracking system. Back then, solar was so expensive, it made sense to track the sun. We went through a phase, probably 10 years ago and before, when it started to really fall away because of the cost of the tracking systems, but we've now seen tracking come back again. In fact, for large-scale solar, tracking is really the way to go because it's very efficient use of land. So sometimes technologies come and go because of various market forces. Now, this is a rather technical looking slide, but if you kind of look over to, see if I can get my little pointing finger going, pointing the right way. It's really funny trying to point. The green line is, let me have a look there. Sorry, the blue lines with the blue squares, either solid or with a white center, are the two most popular types of photovoltaic modules these days. That's polycrystalline and monocrystalline. The monos are the solid blue ones, and the polycrystalline or multicrystalline, same thing, are the blue squares with a white center. It shows you the efficiency on the left-hand side, and you can see back in the 80s, efficiencies of solar panels were 12, 13, 14%. But they've gone steadily up and up and up, and we've had some remarkable steps forward in the efficiency of solar panels through small incremental changes, and it hasn't stopped. So these days we're up into the 20s. I think we're up for monocrystalline, something like 26%. Multicrystalline up to 27, I think. I'm looking around for 23, sorry, for multicrystalline. And that efficiency, it measures the efficiency of area. So don't think it's has a direct relationship to electricity production. It's the amount of power produced per area of the panel. So if you've got a 1 metre square area with 1,000 watts per square metre of sun's energy falling on it, about 20-something% of that 1,000 watts of sun's energy is being converted into electricity. Now, you might think that's not very good. You go, oh, gee, that's pretty terrible efficiency. I wouldn't buy many products that were that inefficient. But you've got to remember it's about the resource. What's the cost of the resource? And in the case of the sun, the resource is free. No one's worked out how to tax the sun yet. So you've actually got a free resource that you're harvesting energy from. The tools for it are the solar panels. Here's a little slide showing the process of different technology developments. We've had PERC cells, which gave a big step up, passive emitter rear collector cells. We had HIT, or hetero-intrinsic thin film, which was a clever idea where they combined two different cell types, one on top of the other. So you had a monocrystalline cell and then a translucent cell made of amorphous silicon on top, and that meant you sort of got 2 bites of the sun's ray. You might think the top layer would mask the layer beneath it, but really at an atomic level, there's a lot of gaps between atoms, and photons often miss completely an atom and pass through to the next layer. So you're getting more yield with multi-junction. But the cost was very high. It didn't really take off, though. It's still in the market and may come back. New kid on the block, perovskite. This has been in R&D for quite a while now, but it's got some very promising characteristics. So it's not silicon. Perovskite is a synthesized material, and efficiencies they're thinking in the 30s, 30% range. What's going for perovskite is it's made at relatively low temperatures, something like 200 degrees Celsius, whereas melting silicon is over 1,000 degrees Celsius. So that makes a big difference on the energy inputs to the material. So it makes it much cheaper to manufacture if you're not having to heat up to such high temperatures. And it's not, because it's a synthesized material, they can make it from readily available industrial chemicals. So that's one to watch. And I did think we'd have commercialization by now, but no, we haven't. We're still kind of waiting on that one. All right, time for some physics lessons. Back to school, everyone. This is about as techie as I'll get in terms of physics. It's the top of my pay grade, is understanding at the atomic level what's going on when when light is generating electricity through the photovoltaic effect. Now here we've got a PN junction. It's some material, some silicon atoms with a small amount of impurities. And the silicon atoms have a special characteristic known as covalent bonding. They'll share an electron. Those little ovals between atoms are the shared electrons, and that forms a very stable, in fact, a insulating material. And so pure silicon actually is not a conductor. It's a poor conductor, and it's very stable, and it's a crystalline structure. That's the characteristic of covalent bonds. But shining light on pure silicon, nothing will happen. So how do we generate some electricity? We give it some opportunities. We throw in a few phosphorus atoms, and we're talking parts per million here, and phosphorus has one extra electron in its outer shell. And that free electron is actually there to be disturbed by energy. And the energy in the form of light, a photon, hits that atom on the outside of the shell and will displace it, cause it to basically leave the outer shell. So it's now a free electron moving, it's electron flow, so you've got current. But it can't move unless it's got somewhere to go to. So if we only doped with phosphorus, that electron would fall straight back into the outer shell. So we introduce some boron, which has one missing electron. It's known as a hole in the outer shell. And so it's ready to receive a surplus electron should one come floating by. And therefore, with the input of energy from light, in the case of photon energy, hitting the phosphorus atom, causing that electron to be ejected from the outer shell and then moving into a hole of a boron, we now have electron flow. It's amazing. It works. So what does that look like at a circuit level? You have a PN junction, which is where you start with a base material. It might be positive type, also known as P-type, or it might be negative type, known as N-type silicon, and then the top surface of it is doped with the opposite type. So it's not like a sandwich. This picture makes it look like you've stuck two layers together with some glue or something. No, it's done at an atomic level. You're basically putting a nano thick layer of the opposite material onto the top surface and creating the PN junction. And the reason it has to be so thin is that light won't pass very far into that solid material. So you actually have to harvest the electrons right on the surface. Nothing much will happen until you've got a circuit. So you might see that we've got a circuit going to something called a regulator, or it might be an inverter or a battery, and therefore we've got current flow. So, in summary, light hits a PN junction, displaces an electron. If there is a circuit, current will flow. Pretty simple. A little bit about the manufacturing process of a monocrystalline cell. And I'm going to explain the three main types: monocrystalline, polycrystalline, also known as multicrystalline, and thin film. So let's start with monocrystalline, because historically that was the first type of cells manufactured. It was done by growing a silicon crystal, basically in a partial vacuum, high temperature, seeded with a seed crystal, and very slowly drawn out of that molten silicon, or what's known as polysilicon, slowly out, and it will form this big long crystal up to about 2 meters long, and it's very shiny. So it looks like a big shiny cigar. It's pretty much perfectly circular if it's well grown with little tapered ends. It's then roughly cut into a square. So you'll notice that the corners still have the remnants of that outside curve. The reason for that is really just about wastage. You could make perfectly square cells from a cylinder, but you'd have to waste a lot of material. It's a bit like squaring up a log. You've got to cut a lot off to get down to a square post. So they just leave a little bit of that chamfered edge as cost benefit. Though I have noticed the chamfered edge is getting smaller and smaller, and also the size of the crystals, the diameter is getting bigger and bigger. So we're getting squarer monocrystalline cells. That wafer then is doped with the opposite material. So if it's an N-type silicon, it'll be doped with P-type and vice versa. And then a conductive grid is applied to the front with some bus bars, which are the thicker conductors on the front of the cell. And the end result of all of that is a PV module. I'll just lean back so you can see it. There it is, a solar module. And they're soldered together. Each cell produces around about 0.5 volt, and the number of amps depends on its size. But these days, your large size cells, which are about 6 inch, will produce about 8 or 9 amps. So 0.5 volt, 8 or 9 amps. And then they're wired up in series to give a useful voltage and put into a panel. So that's the manufacturing process of a monocrystalline cell going all the way through to a panel. Monocrystalline also has very high conversion efficiency because of being made from a single crystal. The other strategy is to cast. Now here I've actually got a picture of a monocrystalline crystal on the left-hand side there, just on the left there. And next to me, a polycrystalline. Now, polycrystalline's made differently. It's not grown slowly. It's actually cast in an ingot. So a large crucible, typically about 700 or 800 kilos of molten silicon is poured into that crucible, and they control the cooling rate to grow the largest crystals. Now, you don't get one crystal when you do it that way. You get multiple crystals. A bit like if you look at a frozen puddle of ice, you can see all the crystallization in the ice. And that's what gives polycrystalline panels their kind of sparkling characteristic, because that ingot is then sawn into perfectly rectangular wafers. And so that's a plus, because now you've got a wafer that packs very well into a rectangular frame. So that's the process of producing polysilicon, but there's a bit of a downside, which is polysilicon has slightly lower conversion efficiency than monocrystalline, 1 or 2% less. And the reason for that is because of all those crystals. Wherever you've got a boundary between two crystals within a cell, that's a lossy zone. So any electrons that are liberated at the crystal boundary are reabsorbed again. So that 1 or 2% loss means their conversion efficiency is a bit lower, but you can pack more active material into a panel, and so you'll find that often polycrystalline panels are about the same power as a monocrystalline panel because they get better coverage. But there is another characteristic, which is their temperature characteristic, their power temperature characteristic. So it used to be, and I'm saying this talking maybe 10 years ago, it used to be that polycrystalline was a preferred option in warmer parts of the world because they lost less power as they heated up, whereas monocrystalline was a more popular choice in colder parts of the world because it didn't matter, because that loss was very small. But we've seen the manufacturing processes and some of the innovations with monocrystalline bring that losses down to almost the same as polys. So these days, mono's really taken over. This is the third class of panel, or solar cell, I should say, known as thin film. Now, it's not a single chemistry. It's an umbrella term for films of photovoltaic material applied to a substrate. And it might be plastic, like this gentleman from the CSIRO is holding up. It might be a metal substrate or even glass. The advantages of thin film is the fact that it can be applied to all sorts of materials, and it can be applied so thin that it's even translucent. You can see through it. You can actually, and you have been for decades, be able to buy solar windows that you can see through. They'll still generate electricity because they don't actually need to be opaque to generate electricity. It's, after all, only a few nanometers deep that the p-n junction is useful. It also means you can do things like multi-junction, where you've got a crystalline silicon layered with thin film on top. That's another plus. And in the case of being applied to materials like plastics, they can be flexible and can be rolled up. But there is a disadvantage. And the disadvantage is their conversion efficiency is generally a lot lower, about half or less of a crystalline cell. So they've sort of faded from popularity. They're a very niche part of the market these days, but they are found in things like calculators, wearables, and there's some innovation to make super low-cost PV cells that are kind of temporary cells, printable PV cells. You can literally make them with an inkjet printer at home and some acetate. They probably won't last very long, and I don't know how you could wire them up safely, but there you go. You can actually make printable thin film panels. Getting a little bit technical again, just understanding the differences between how the sensitivity to light is affected by different types of solar cells. Now, on the right-hand side here, the legend gives different colors for different types of solar cells. CSI, no, it's not crime scene investigators. It's crystalline silicon, so that's the brown line. Then we've got ASI, which is amorphous silicon. That's a type of thin film. It's basically silicon, but in a thin film coating, atomized at high temperature and coated onto a substrate. The green line just shows you what we can see. So the spectrum of light that we can see. So solar cells are much more sensitive to a wider spectrum than our eyes are. They'll pick up to the short wavelength and the longer wavelengths. We've got a couple of outstanding cells there, the galliums, the gallium arsenide aluminium and the gallium arsenide. They have an enormous range of sensitivity and their sensitivity to very low energy photons. It's known as their band gap energy. And that means they'll produce a lot more electricity per square meter than a crystalline silicon cell will. So you might be asking yourself, why would I use crystalline silicon if gallium arsenide and gallium arsenide aluminium are nearly double the efficiency? It's because you can't afford them. Something like $1 million a kilowatt for gallium arsenide. And that puts them into a special category, which is outer space, literally. Also, gallium melts at about 30 degrees Celsius, so you want to keep them pretty cool. So once again, space is a great place to keep it. And the cost isn't such an issue when you're launching a satellite. You want the most power per square meter from those solar panels. So those rare earth materials aren't used on everyday systems. So leaving behind the heavy theory for a moment, the future. What does the future look like for the solar industry? In fact, what does the future look like for homes and energy? Now, this picture is one of my favorite pictures. It's of a city in Tokyo, a city 80 kilometers north of Tokyo called Ota City. And Ota City, back in the early 2000s, I think this picture was taken in 2006, had a problem. In fact, they had the problem before 2006. The problem was it's a satellite city to Tokyo. That means people commute back and forth. And it grew very fast, faster than the electrical infrastructure, the main transmission lines to this satellite city could be rolled out. And so as a result, the utility was faced with, what do we do? Do we invest heavily in upgrading transmission lines, which can take a long time, and planning issues, etc.? Or do we look at other ways of reducing that electrical demand? Now, obviously, the first thing is literally reduce demand. So they ran an energy efficiency program, probably things like CFL lights back in the day, but that only trimmed off a small percentage of the demand. And this is north of Tokyo. It's very cold in winter time, so there's a lot of electric heating goes on as well. So they actually subsidised, I'm not sure to what level, whether it's 100% or not. Anyone who actually knows, let me know in the comments. I did actually have a student who was who did his thesis on this town. I really should have plugged him a bit more for the numbers. But the utility funded most of what you can see there. So almost every house got solar, and many of them got batteries as well, just to reduce electrical demand and offset the investment in transmission line infrastructure. Now, jump forward 20 years-ish, and here we are with solar panels costing a fraction of what they did back then. In Japan, which is a protected market, that means you have to buy Japanese-made solar panels in Japan. They were probably $15, $20 a watt back then. And now we're looking at sub $1, sub 50 cents even a watt. So solar has become so much more affordable and therefore so much more appealing to utilities as offsets as well. So I call it the future because I see the future of many residential homes as being autonomous. That means energy autonomous. They can produce and store and use most of their energy. They may still have a grid connection. I'd like to think of it as the legacy connection to the utility grid that they use as a last resort. Because the size of most freestanding homes is adequate to provide enough power to power a typical home. Somewhere around the 20-25 kilowatt hours per day is not too hard to achieve on most freestanding homes. So that's pretty exciting. But there is another use case for solar that's coming along now, which is network upgrades. Now, this is actually a picture from a system that I designed and my electricians installed. It was a customer who just wanted more. He was on the grid. He used a lot of power and he wanted more, and fair enough. So he did the obvious thing, went to his electricity company and said, look, I want more. And they said, well, you're on a swirl line, a single wire earth return. You've got a split phase transformer, 10 kVA per phase, one to the house, one to the packing shed, and you're basically maxed it out already. This customer was up around 180, I think, kilowatt hours a day of consumption, and they needed more. Well, they couldn't get more over those wires. So they got a quote for an upgrade from the utility, and some very, very, very big numbers came back because they basically had to go to three-phase and run a lot of aerial wires down the streets to their property. And so the budget was so high that actually it was cheaper to build a massive solar and battery storage system. We're talking 46 kilowatts of solar, 300 kilowatt hours of batteries, coming in at probably about half the price of the utilities quote to upgrade the poles and wires. And of course, the difference is no more bills, pretty much, once you've installed that system. So this is a case of fringe of grid, or in this case, on the grid, but wanting more. And they went from single phase or split phase, which is pretty awful, to three phase as well. So we gave them a much more functional system with much more capacity. So around 45 kilowatts of continuous three-phase power, 300 kilowatt hours of battery storage. That picture, by the way, is a construction photo. All those batteries are fully covered in by now. So that's just giving some real-world applications of solar. It's not just about exporting it to the grid or reducing the cost of electricity. Sometimes it's completely displacing the utility. And what we're starting to see is a few customers even leaving the grid. I don't think it's a very viable option in terms of return on investment, but it's free country so far, so people are sometimes choosing that. So coming back to theory, I want to talk a little about the terms that we use in the solar industry. And we talk about energy and power. And the terms often get mixed up a little bit because a watt hour and a watt are actually quite different things. So I'm going to explain that in terms of PV. So we measure the energy from the sun in watts per square metre. And here's a little graph showing the watts per square metre on my house in, when was it taken? In 16th of February 2015. So that's a solar radiation meter up on the roof of my house. So in the middle of the day, it got up to around 1,000 watts per square metre, and you can see it tapers off in the afternoon, and it must have been a bit cloudy in the morning. So it's not an absolute peak, it's a sort of an approximate peak. If you're in a higher altitudes, it'll be a little bit higher, and if you're in places where there's a lot of reflection from the earth, like snow, that reflection's known as albedo, that will give you even higher radiance. And sometimes clouds too. Certain types of clouds will reflect a lot of light and give you some very high readings, maybe 1,200 even watts per square metre. The things that affect irradiance is air mass. Now that's a kind of technical term for the thickness of the air and the way it changes the colour of and absorbs and scatters the light. The latitude, which really is the biggest factor, where you are with respect of latitude from the equator. The closer you are to the equator, generally the better the solar resource, though there are some local climate factors like clouds, those nuisance clouds, can also moderate that. The time of day, obviously, in the morning the sun's low, in the middle of the day the sun's high, and the season, the angle of the sun. And the further you're away from the equator, the more that variance occurs. You get here in Melbourne, the sun will peak at about 74 degrees above the horizon midday, and in wintertime only 28 degrees above the horizon. So that change of angle means that less rays are basically getting to your solar panels and more light's being absorbed into the atmosphere. The energy from a solar panel, or from, in this case, directly from the sun onto a surface, is measured in watt hours per square metre. Not watts, but watt hours. Remember, it's over time. And here's two plots showing at the top summer and at the bottom winter. Now, you might look at that bottom graph and think, oh, that's a lovely day. It's such a smooth curve. But look at the peak. It's only 550 watts at the peak, whereas the top one is actually just over 1,100 or so, nearly 1,200 at some point in the day. So in summertime, we're getting higher peaks, longer days, and therefore more energy. So per square metre, we're getting in summer about 9.6 kilowatt hours of pure energy from the sun. Remember, a solar panel will only convert about 20% of that. What affects the amount of energy striking the surface? Well, I did mention clouds before. Most of the energy comes as what we call direct solar radiation, direct beam. So a beam straight from the sun, straight to your panel. That's about 80% of the energy on a sunny day. But we've also got reflected energy, reflected light, scattered light, and diffuse light coming from different directions. So bouncing off the earth is albedo, through clouds is being diffused, and then we've got dust particles which scatter it. So about a 20% overall is that diffuse factor. Now, on an overcast day, it's all diffuse, so that direct beam is gone and you're just relying on the diffuse light. You might notice there is an absolute there. It's called the solar radiation at the edge of atmosphere. That's 1,367 watts per square metre, and it's known as the solar constant. I always laugh when they say that because it's not constant. It varies with the distance of the sun from the earth by about 50 watts. From summer to winter. But it's the peak. And if you start to see people promising you more than you could possibly get, they might not be considering the panels that are installed on Earth, they're installed in space somewhere. Just a reference to some dodgy companies and their estimates. So, why does tilt matter? Tilting a solar panel so that it's perpendicular to the incoming rays will give it the biggest target to the sun. Therefore, the most rays will be captured, the most energy will be produced. And here I've shown a difference between a panel at perpendicular to the sun versus one that's flat on the roof, horizontal. And in this case, of the 12 rays that could have hit the panel when it's in the perpendicular position, when you lay it down, only 9 rays hit it. So that's why you get less performance in wintertime, because more of the rays are basically missing the solar panel, and also the angle means that you'll get a bit more reflection, particularly at the ends of the day. A little bit of technical terms here. Now, because this is a slide deck, you can go back through these and have a look at this, but I just want to introduce the terms that we use. So solar radiation can be measured, and organisations like in Australia, the Bureau of Meteorology, and in New Zealand, NIWA, at the weather stations scattered around the country, measure this. It's also measured by satellites globally, and there are websites that can report that too, which are quite useful for doing designs outside of your region. The terminology used to measure the energy from the sun is megajoules per square metre. Now, the reason for that is that a joule is the natural unit of energy, but from an electrical perspective, it's much easier to work in kilowatt hours per square metre, so we just convert by dividing by 3.6. So if you do get your data in megajoules, just convert it by dividing it by 3.6, and that'll give you kilowatt hours per square metre. You'll see in a minute why that's useful. But actually saying kilowatt hours per square metre gets a bit tiring, especially after a few beers, so we tend to shorten it to peak sun hours, even shorter to PSH. Now, peak sun hours, or PSH, is not a SI unit, it's just shorthand for kilowatt hours per square metre. And it can be measured on a daily basis. So an example here is actually Melbourne. Melbourne has an average solar radiation over the year of 4.75 peak sun hours. It's very similar to Auckland, actually. Now, this is an example of a solar radiation table for Auckland. I actually generated this one for Manukau some time ago. And what you're looking at there is, on the left-hand side, is the compass bearing. So 0 degrees is true north. So degrees on the left, 0 degrees is true north, 180 degrees is directly south, and going around the clock, 90 degrees is east, and 270 degrees is west. So that's basically a way of using this table to calculate the amount of energy falling on a surface, not allowing for shading, by the way. So I've colorized it to give you a quick and dirty, it's good, it's bad, it's ugly, and so green, yellow through to red being poor, and the numbers represent the number of kilowatt hours per square metre averaged over the whole year. So it's an annual average. Now, that's a useful table when you're designing a grid-connected system, because you might produce more energy in summer and less in winter, but the averaging is kind of what the benefit is all about, though there are some other factors. But it's worth also noting that what the orientation of the roof is, how much better it could be or not. Now, I've looked at this graph a few times, and I can see the biggest number, this table, sorry, on that page is 4.41. So around about 10 degrees to the west of true north at 20 degrees of inclination, so your standard sort of roof in Auckland, it would facing true north is just sweet as. It's really giving you the best possible performance. But if you don't have a perfect roof, let's say your roof faces east at 20 degrees, which in this case is 90, it's only a little bit less. It's 3.88 peak sun hours. So it's going to work a bit better in the morning and a bit poorer in the afternoon, but it's still very, very good. So you can use this as a simple guide to percentage. I should point out, though, there's better tools than this, and just to give a plug for my software that my company produces, Solar Plus, we have all the solar radiation tables for New Zealand as well as Australia and other countries. So you can actually use software to generate a full design from woe to go. Now, this is a device for measuring the degrees of shading on a surface. Now, those tables I just showed you are about the amount of energy falling on an unshaded surface. But when you are trying to calculate the amount of energy from a real installation, you've got to allow for shading. And something that can give you a reasonable estimate of the seasonal variation in shading. Now, this particular device is very, very simple. It's really just a hemispherical plastic dish with some lines behind it. It's called the Solar Pathfinder. I don't have any commercial arrangements with them, but I have used this for a couple of decades now, this product. It's solarpathfinder.com. It's a fairly expensive piece of plastic, but it does the job quite nicely. And there's even some software for it to help you with your analysis. But if you look at this picture, you can see that I'm looking down into this view of some trees and some sky, and there's not much sky. If you're wondering about those numbers across the bottom, that's the time of day. So on the right-hand side, 9 o'clock in the morning, in the middle of summer, the sun just gets over those trees. And then we get a good, 6 hours of sun in the middle of summer, and it sets at like 4 o'clock behind the trees. And it's doing it right there in that picture. But check out wintertime. In June, it doesn't even make it. It actually never gets above the trees in June. So really, the solar window, which is the area not obscured by the trees, it gives you an idea of the useful energy from the sun. And so you can use a tool like this to derate your theoretical amount of solar energy. I should point out that for many grid-tied systems, this is not a big deal. People don't get that excited about doing site assessments and giving very exact estimates. But if you're going off-grid, there's no approximately is good enough. It's got to be good enough. You can't approximately have enough lights on. You need the lights to stay on. So you've really got to calculate the performance for all seasons. Getting to the end today, and I keep looking over at the comments, and then there's no questions. There's just a thank you, David, for saying hi. So feel free to throw some comments and questions in while we're going live. Now this is what's known as a voltage current characteristic curve for a solar module. In fact, it's quite an old one. It's an 80-watt module, so not many of them about anymore. The curve shows you the difference in performance as voltage changes. And so a solar panel will produce the highest voltage when there's nothing connected to it. We call that voltage open circuit. So that's over there on the right-hand side. It's about 21 volts or so. When you short circuit a solar panel, nothing bad happens. It doesn't blow up. And you put it in the sun. It just doesn't produce any voltage, but it produces current. So that's current at short circuit. And between those two is the sweet spot where you'll get the most power. And that's generally on the knee of the curve. In this case, at about 17.5 volts, 4.6 amps, we're getting the maximum power out of that PV module. And that is the job of an inverter, is to find that sweet spot, or a maximum power point tracking charge controller. It tries to find that sweet spot and operate the array. Remember, the array doesn't push power into equipment. Equipment like inverters and maximum power point trackers draw the power from the panels by operating it at a particular voltage and current. Oh, I've got a question. What's your email address, mate? Actually, I don't give emails out on live YouTube, but you're welcome to go to my website, smartenergylab.com.au. And there's a form on there you can send me a message. It kind of stops a lot of spam. Thanks very much, Sean Clark. So temperature. It's the other one that has a big impact on solar panels. I mentioned this before, that solar cells are sensitive to temperature. That means as you increase their operating temperature, their power goes down in terms of theoretical power. And a solar panel is tested and measured at one particular temperature, at 25 degrees Celsius. And we call that standard test conditions. It's the temperature that's convenient to test stuff at in a lab. It's not too hot, not too cold, but it's not very real world. You might think, oh, well, today's a mild day, it's probably about 20-something. But the solar panels won't be at 20-something. They'll heat up like metal does. And actually, just to illustrate this, I might just jump over, see if I can do this elegantly, to my computer. So we'll just jump over to my computer. Here we go. So this is a log of temperature of a solar panel. Now, what you're looking at there, I've just got to scroll back out a little bit, is in green is the temperature of the cell, of the module, and in orange is the temperature of the air. And you'll see that, this is on the roof of my house just a couple of days ago, that the cells only got up to the air only got up to 9 degrees in the middle of the day, but the panels were peaking up at over 20. So a panel heats up a lot more than the ambient temperature, and therefore it loses a lot more power than you might think because of that transition. So I'll just go back. Here we go, back to me. Here we go, temperature derating. So you've got to allow for this in real world conditions, that the solar panel will actually produce less power under normal operating conditions unless you're lucky enough to live somewhere where it's below zero most of the time. So that temperature derating is given in percentage per degree Celsius above the test conditions. And so you're losing around about 0.4% per degree Celsius per degree above 25, which is the test conditions. Oh, Chris has got a little question here. Let me just bring Chris on. So Chris says, can you talk on adding panels together on different wattages, voltages? A couple of 285 watt modules with a few 310 watt modules. Thanks, Chris. I think I know what you're talking about here. So you've either got a system that's had a fault and you're trying to replace some of the modules with some new ones, and you can't get the same wattage anymore, or you've got a system that you want to upgrade in some way, so you're adding a few modules. This is a very real world problem. So Chris says, I know the answer, but I'd like some more knowledge about the subject. So thanks for that, Chris. I'm just going to draw a little answer for you. So let me just drop that off the screen, and I'll jump over to my drawing tablet. Now, I haven't done this one for a bit. Here we go. Let's have a look. So here is the problem. The problem is that the existing system may be made up of a group of solar modules. So this is the symbol for a solar module, like this. Okay. And typically you'll connect them in series. So the positive of one will connect to the negative of the next, like this, to get higher voltages. Now, that's only 4 panels. Most grid tie systems will be certainly a lot more than 4 panels, but there we go, it's simpler to draw. Now, these might all be 285 watt modules. And either one of them is faulty or you want to add one more to the system. Can you just tack on another one that's actually a bit bigger, right? So we're putting a 310 watt module on the end. Can we do that? Well, there's 2 considerations. Are you allowed to do it legally, like the standards, or the standard for installing solar PV systems in Australia and New Zealand is AS NZS 5033. That's the PV installation standard. It's for both on-grid and off-grid. It's basically just for PV systems connected to anything. When you're adding panels in a string, you are increasing the voltage. If you add a bigger panel, it depends on how many cells it has, whether it's how much voltage it adds, but more importantly is the amount of current that it can produce. Now, what you don't want to happen, and it's all about current. Let's say these panels have an operating current of 8 amps. Okay, so these are all 8 amps. Right? And this 310 watt module, even though it's more powerful, might actually have smaller cells but more of them, and therefore a higher operating voltage. So it gets its higher power by having more cells. So it might be a 72 cell module, where these might be 60 cell modules. So let's say this one actually produces only 7 amps, but at a higher voltage. Now, if you know your electrical theory, current in a series circuit must be constant. You can't have different currents in that series circuit. So that means that all of these ones will be pulled down to the lowest current in the string. Now, that doesn't damage them. It just means that you're throttling them a bit. So the problem with adding to an existing system is if you're not putting in a panel that has the same or more current generating capability, you're going to throttle the rest of the string. So let's say this had 10 amps. That means that all these will work at their maximums again. Okay, great. But 10 amps can't be done. It'll drop down to 8. And so it'll work. We've got the right number of, so we've got 8 amps coming out of all those panels, but our 310 watt panel is probably going to drop down to 285 watts. So we don't actually get 310 watts out of it, but it's still fine. There is one more consideration, is are you exceeding the maximum voltage of the equipment? So what is the voltage open circuit max? Now you've added one more panel in the string, and therefore the voltage will have gone up by the addition of that one panel. So make sure that that's not exceeding the rating of the product that you're installing and connecting it to. So hopefully, Chris, I answered your question there. So just jumping back to, where are we? Yeah, so that's good to get some interaction. Thank you, guys. So how are we going there? No more questions, I think. Oh, yes, Kieran. Kieran, is that an example? Where does the extra 1 amp of current go to? Into heat. Thanks, Kieran. So it's one of the biggest misconceptions. I'll just add that question to the screen there so you can see it. One of the biggest misconceptions is that the solar panel has to produce power. It doesn't have to produce power. The inverter chooses the amount of power the panels produce. So think of a solar panel as a current source that will deliver up to its maximum depending on what the load requires. And an inverter or a charge controller can choose how much current to draw from that panel. So in the case of adding that extra panel into that string, the extra amp never gets produced. You're actually operating the panel at an inefficient point on the IV curve. In fact, this is probably a good reason to jump back to this slide. I'll just go back one slide, where I actually had a picture of the IV curve. So here's the IV curve of a solar panel with different irradiances. I'm going to go back one more. I don't have to operate at that sweet spot where I'm going to get 80 watts and 4.6 amps. I might choose to operate at a higher voltage and therefore less current. So that's what happens. The panel actually is operating inefficiently, and therefore that extra amp isn't produced, isn't lost as heat, doesn't go anywhere. Great question. Thanks, Kieran. So just go forward on that. So I did mention temperature. Here's a graph showing temperature. What we've got here is a panel at 25 degrees Celsius. When it is at 25 degrees Celsius and in full sun, we'll be operating at what's known as standard test conditions. And as I said before, unless you live somewhere where it's basically freezing, your panels will never be operating in full sun at 25 degrees Celsius. Most of the time in New Zealand and Australia, they'll be well up above 50, even higher in midsummer. So they're going to lose some voltage, and that's what means that's where the power goes. They're actually producing less voltage the hotter they get. Conversely, the colder they get, the more power they produce because they produce more voltage. Now that's a good thing if you're lucky enough, but it is a consideration in terms of safety. The equipment that you connect it to must be able to cope with that higher voltage under cold conditions. It might be quite fleeting though. You might find that just first thing on a cold frosty morning, the sun comes through the fog at sort of 10 o'clock, the panels are at 0 degrees, the sun hits them and you get the maximum voltage for a few seconds. Does it damage any of the equipment? Does it exceed the rating of switchgear and cables and isolators, etc.? So that's really more of a concern for selecting product than actually getting a bonus of power production. But if you happen to live somewhere where it's 0 degrees, good on you. You'll really get a lot more power out of your panels. So lastly, I just wanted to explain, and I think this is actually relating to Chris's question about series and parallel circuits, that if you have panels in series, the voltages add together, but the current is constant. So you don't get any more current in a series circuit by adding more panels. Conversely, in a parallel circuit, when you parallel panels, you don't get any more voltage, but you get more current. And we generally build systems, certainly larger systems, using combinations of series and parallel. So you might have 2 strings of panels, identical number of panels, parallel together to double the current, but maintain the same voltage. Like this. So here we've got a series and parallel circuit. So how are we going, everyone? We're getting close to the end of today, and I'm just looking across to see if there's any more questions or comments come up. So feel free to type those in. We've got a couple more slides to go. So one of the issues that does happen with multiple panels connected together in combinations of parallel and series is when you get shading across single modules or a partial shading across an array. It doesn't take much to cause a solar panel to stop working in a string. And you might think that's surprising that, putting your hand, literally your hand across one cell on a panel will have a significant effect. It may even, if you put your arm across the short side of the panel, turn the whole panel off. And that's because they've got a safety feature. I've shown it here. It's called a bypass diode. That bypass diode is there to protect the panel from dissipating too much heat when there is shading on the panel. Because actually when you shade a panel, instead of it being a current source, it actually starts to resist the flow of current. And therefore, if it's in a string, the rest of the cells in that string are pushing power through that resistive circuit and heating up the cell. I've come across faulty panels where a bypass diode has failed, and the cells are too hot to touch when you put your hand on them, because the shading of my hand causes the cell to heat up. So it's very, very noticeable. So that bypass diode is built into the modules. It's a requirement of our standard, and all modules have them built in these days. Once upon a time, you had to fit them yourself. You got a little plastic bag full of diodes, and some people go, what are these for? Oh, throw those out. They are the safety features to prevent against overheating during shading. But when you do have a solar panel, and generally they've got multiple bypass diodes, so that might be 2 or even 3 sections within a panel that are bypassable, you will lose voltage. So when the bypass diode starts to conduct due to shading, you lose voltage. And that means you're going to, in this case, have 3 strings of 3 panels. In one string is shaded, the bypass diode starts to conduct, and it'll depress the voltage across all of those strings, because the voltage at the common point, Kirchhoff's voltage law, by the way, for those engineers out there, has to be the same. So it means that a small amount of shading can have a disproportional effect on modules. Now, there are ways to overcome this. Good design, multiple inputs to an inverter which have separate maximum power point trackers, module level power electronics such as microinverters or so-called optimizers, which really overcome this loss due to a module being bypassed. But if the site doesn't have shading or doesn't have significant continuous shading issues like a panel behind a chimney, then it's not really a big deal. So this is the last of my slide deck, just showing all of the panels now being shaded, and so they've actually taken themselves out of circuit, and therefore we've lost 1/3 of our production. So you can test this pretty easy, by the way, if you've got a PV array with multiple strings or even just one, with a clamp meter, but you'll need a DC clamp meter. So that's probably for those who are installers out there or electricians, is one of the things that is a basic tool in the solar industry is a DC clamp meter. It's not a tong tester like you might use for AC. It uses the Hall effect. It's a different beast, and it's a lot more expensive generally, but it can measure DC currents, and you can use it without having to interrupt the circuit. So you don't have to run current through your meter. You're literally clamping a DC clamp meter around a cable, and you can clamp it around that cable and just directly measure by shading the panel and seeing how much current it drops. So that's quite a fun thing to do. Well, we've come to the end of today's session. So thanks everyone for your questions, comments, and time, and thanks Kieran there for that last question. I just want to bit of a shout out to all those in lockdown in Auckland, well, basically the whole of New Zealand to some extent, and greater Metro Melbourne, because I'm in Metro Melbourne area as well. I know how you're feeling, but we'll get through this. Keep safe, keep strong, and hopefully I'll see you again tomorrow when we're going to do Friday live streaming, 5 p.m. New Zealand time, 3 p.m. Australian time. Hope to see you then. Thanks everyone.